Hello everybody, I'm Paul Terry, I'm the CEO of Photonic. I've been asked to speak for the next 10 minutes or so on scale and what quantum is in scale. So I'm going to try to be contentious and leave you with a couple of ideas here. Just by way of background, my first 20 years in this business was to build the wide area networks for North America and Europe, which we did, which are very big scalable items with hundreds of thousands of nodes and protocols. And then we sold that company, and then we built a supercomputer, and I was the CTO of Cray. So we used to build large supercomputers, 100,000 processors. So I've spent 40 years in the world of scale. So I'm going to try and share very quickly what scale is and what it means to quantum. Okay, here we go. So first of all, let's start with the definition of scale. Everybody gets this wrong. So what is scale? So scale is basically making the marginal cost of adding one more thing to something zero. So if you add one more thing to something and the cost is the same as the last thing you added, or it's higher, things get bigger, but they don't scale. So your marginal cost needs to be zero. What that does translates into quantum world is the marginal cost of adding a qubit to a computer or a network of computers should be zero. An example of this would be, of course, the internet. Adding a router to the internet, the marginal cost is zero. OSPF, BGP4, those protocols were designed so you could actually scale a network and do so without a central authority, etc. So that's the definition of scale. It's a very difficult thing to achieve. It's a very insidious thing. Little things get you when you scale something. In the world of quantum, let's bring it back to quantum, there are two types of scale up and scale out. So scale up is ever more numbers of qubits in a box, or a unit, or a system, whatever constraint that you have. So if you have a cryostat, if that's your constraint, or a vacuum tube, how many qubits can you get into that box? That's a scale-up approach. Okay? A scale-out approach says, hey, whatever you do in terms of putting numbers of qubits in boxes, how many boxes can I wire together to get a bigger box? In my experience over all these years, people always want more, not less. So what you're starting to see now in the quantum world is we've moved away from single, 2 or 3 qubits to multiple qubits per box, to thousands of qubits per box, to multiple boxes. And there's this move towards, if you like, networking quantum computers together to get a bigger box to move. Just one factoid for you is that the world is going to be, applications in quantum will require between 100 and 2,000 logical qubits. That's going to be the sweet spot of quantum. There are applications below 100, there are applications above 2,000, mostly national security applications. But most of them are going to be 100 and 2,000. So whatever box you make and whatever boxes you connect together, you want to be able to run 100 to 2,000 logical qubits for a second, a minute, an hour, a day, a month to actually run your applications. That's where we're aiming, and that'll be 80% of the market. I firmly believe that by 2030, we will have at least 50,000 logical qubits in service. So notice I'm talking about putting qubits into service, coming from the world of telecoms, coming from the world of supercomputing. We don't talk about processors, or in this case qubits. We talk about what resources do you have in service from which I can run my applications. And that is going to be a change, a maturing, if you like, of quantum from the academic world to application-specific, what are you doing for me today type world. When I was in Cray, I ran 200 application engineers doing applications on supercomputing. Because who cares about a supercomputer? What I care about is, will it run my weather forecasting quicker? Will it run my simulations quicker? That's what matters. And so we're starting to move towards that as qubits become less interesting, and actually multiple qubits running to do something useful becomes more prevalent. I mentioned this from 100 to 2,000 logical qubits. These are the applications that you're going to see. The smaller number of logical qubits, the 100 to 400, is the AI world. Oddly, my PhD, in fact, was in AI 100 years ago now. You don't need that many qubits to do AI. A couple of hundred logical qubits will do AI for you. So we're going to see a market where we will train logical language models against 200-300 logical qubits, mostly in the world of chemistry to start with, and then we'll move on to the world of finance, but it'll both be chemistry. So AI is the degenerate application for quantum, oddly. Okay, everybody thinks it's going to be the most complicated. It isn't. It's the least complicated. When you get to 1,000 logical qubits, now you don't need AI anymore. You don't have to guess what the answer is. You don't need a heuristic. What you can do is you can calculate the answer. And given chemistry is a quantum sport, so when we did chemistry at school, what we're doing is quantum, right? So when you're joining molecules and stripping atoms and stuff, you're doing quantum mechanics. You don't know it, but you are. Now, to model chemistry on a quantum computer requires about 1,000 logical qubits plus or minus 200 logical qubits. Okay? And we can model the world's most complicated metabolites and so forth with 1,000 logical qubits. Going above that to about 1,500 to 2,000 logical qubits, you start getting into the world of finance. That's what they need. Okay? And what's happening right now, by the way, is as we're starting to understand the algorithms, the number of logical qubits we need is actually declining, not increasing. So as we get better at it, it's actually coming down, not up. Okay? There are applications above 2,000 logical qubits. These are mostly national security applications, which is, if you like, beyond the scope of this particular conversation. So that's where we're aiming. 100 to 2,000 logical qubits in service that people can use. The other thing I'll mention is that the idea of selling a quantum computer to somebody is nonsense, right? You don't do that. What you want to do is make quantum services available for people to use. What you want to do is have the Fortune 10,000 be able to access a quantum service like they operate a database service today, for example, or those types of services, right? That's what's actually going to happen. And so the race is going to be to put qubits into service for people to consume. And frankly, the customers wouldn't give a flying anything about what modality that quantum bit is, as long as it's actually doing the job for them. And that's where we should be thinking currently. Okay. Now, just in case people don't know, not all logical qubits are made the same. Okay? Logical qubits have different abilities, if you like. So we've called the lower ones bronze logical qubits. These have error rates that are in the 10 to the minus 4, whatever that means. Okay? Up to gold logical qubits, which have error rates about 10 to the minus 12. The national strategy of the US and the UK and Canada now is to get to gold standard logical qubits by 2033. That's the stated intent of those three nations. Most applications I just mentioned only really need silver logical qubits. But when you hear the word logical qubits, they're just not all made the same at all. And the ratio of physical qubits that you need to make the logical qubit varies depending on the quality of your logical qubit and, frankly, your error correction codes that you choose to deploy. And the objective, by the way, of error correction codes is only to combine some physical qubits to make a logical qubit. That's the only function of an error correction code. So people don't talk about the quality of logical qubits, so I just wanted you to kind of understand that that's actually a real thing, and different applications require different logical qubits. Okay. Now, if you don't know this, and I'm going fast here, so you're doing really well, the game of quantum computing is all about entanglement. Entanglement is the resource that you use in quantum computers. Okay? It is, if you like, the currency of quantum computers. The only question you have to ask any quantum computing company is, how do you make entanglement? Question number one. And how do you consume it? Question number two. Okay, that's it. It doesn't get any more complicated than that. In fact, I was on stage yesterday saying quantum is actually quite easy compared to supercomputing, frankly. I actually find it not trivial, but it's actually a degenerate form of supercomputers. It's actually quite straightforward. So what you're doing here is you're consuming entanglement. There is a concept called a universal gate set, which means, if you like, the logic gates that you can do in quantum computing, which are akin to, metaphorically similar to, AND gates, OR gates, and NOT gates in classical computing. In quantum computing, there's arguably 16 of them. Every universal gate set can be achieved using entanglement, by consuming entanglement. So the question you have to ask is, how fast is your computer, and how do you make, and how do you consume entanglement? That's it. Okay, and entanglement is the only thing really that separates a quantum computer from a supercomputer, is the ability to have and create, use and consume entanglement. This is how we do it. We actually use this thing called distributed entanglement. We take two molecules in two different computers, two different cryostats. They both emit a photon. That photon is entangled with the spin qubit it leaves behind. Oddly, if you intersect those photons on a mirror, the photons become entangled, and they project the entanglement back to the spin of the electrons they leave behind. This is a bizarre phenomena, okay? And people say to me, I don't believe you, and I don't blame them, frankly, right? But this is actually entangling two physical objects that have never met each other, right? So, and this can be done on a network. So this is what we do. I'm not selling photonic here. This is just what we do. This mechanism, by the way, won the Nobel Prize for Physics in 2022. So if people are in doubt on this mechanism works, it happens. And this happens between pairs of electrons in a network all at the same time. So you can do embarrassingly parallelism, what's called embarrassingly parallelism. It's not embarrassing, it's just the name of it, in networks. So in high-performance computing, parallelism is the name of the game to get a performant quantum computer. So it's not enough to have a qubit. It's not enough to have a logical qubit. It's not enough to have a logical qubit of a certain quality. What you actually want is a performant computer that's doing everything in parallel. So by virtue of a metaphor, if you look at GPUs, which are parallel computers, then they do things quickly because they do everything in parallel compared to a GPU, which does things monolithically. So this comes back to scale. So scale is how do you put your qubits down? How do you join them into a network? How do you scale them? What is your parallelism, and how fast will you actually give me an answer to a problem? That is the nature of where we're headed, and this is a 2 to 3 year job now. Okay, I don't know if this will actually play, but we can try. Let's see if this will play. Oh no, it does. Magic. So this is routinely what happens in every clock cycle in one of our computers. Every electron in every molecule of the T centers, as we call them, issues a photon. They all entangle with other photons. It all happens at the same time. And actually the application of a program is just to consume that entanglement. A really interesting thing that should keep you awake at night would be the idea that you only need a network switch. We do this, by the way, across a telecom network. The only reason you need a telecom network is to create entanglement. To consume entanglement, those qubits don't have to be connected anymore, which Einstein had a real problem with, but it is actually true. So you only need entanglement to join things together, just for fun. Okay, so speed, entanglement, and operating system. We're going to see, and people talk about this, the qubits to me are actually almost boring now. I'm much more interested in the operating systems that can do parallel entanglement across multiple qubits, across a network fabric, be it in the same city, different city, same chip, different chips, at speed. That's what keeps me awake at night. That's what I care about, and what operating system will do that. And that's what we work on right now. And that was 15 minutes fast and furious. How was that?